All right. So the next topic we're going to talk about, the next couple chapters are sort of standalone chapters. Um, and they're about topics that obviously we're going to apply mechanics to. Like today, we're going to talk gravity. And in the discussion of gravity, we'll still talk about conservation of energy and potential energy and, and forces and all that kind of stuff. But it's not directly related, like in progression, to what we've been doing. And we'll see that also with the next chapter after this, which is about fluids. Same kind of story. We'll apply all the things that we've done, but it doesn't really, it's not following that linear progression. But let's talk gravity today. Basically how it works and why we get the numbers that we get for gravity, like on the surface of the earth with the 9.8 meters per second squared and all that. So I'm just curious, what do you guys know about gravity as in universal gravity, not just on the surface of the earth?
Space time.
Okay, so it's related to space and time. And I know that I don't remember who it was, but somebody brought this up weeks ago about Einstein's theory of relativity, and it definitely ties into gravity. I see Victor just typed in, it's a weak force. And it actually is, surprisingly so. We tend to think that gravity is really strong from our day-to-day experience. And for us, the gravitational force is pretty strong. But when you learn more forces later, you'll see that, like, compared to magnetic forces, electric forces, gravity is pretty darn weak.
Isn't that like a big problem with like making a standard model, is that gravity is a weaker force than it should be or something like that? Like it's really weak in comparison to the other forces?
I don't know about it being a problem for constructing like the mod. I think you're talking about like a unified theory model. Is that what you're talking about, Jacob?
Yeah.
Yeah. So I don't know if its relative weakness is the problem there, but it is something that is a bit surprising how weak it is. Victor, no, I haven't heard this. He just put in the chat that he read once that that they think gravity came from a different dimension, and that's why we're only getting part of the force. Now, I've not heard that before. That's very intriguing. I will definitely tell you. Obviously, also understand that I'm not a physicist, right? So I don't practice it. So I'm not up on everything. I do, of course, read about it. I tend to specifically read about astrophysics. I'm on a couple of listservs with like JPL, the Jet Propulsion Lab, and NASA and stuff like that. So, but no, I've not heard that gravity may come from a different dimension. That would actually explain a lot. Like one of the things, I'll just go ahead and share this with you now. I usually talk about this in the fourth quarter, is that all forces, we think, have some sort of a mechanism for that force going between two objects. So for example, electromagnetic force, the particle that causes that to happen are photons. You might have heard of those. Photons are like the little particles of light. So there are photons, there are bosons that are used for nuclear forces and stuff like that. And so there's a proposed graviton, which would be the particle that actually goes between objects that allows gravity, the gravity field force to exist. We have not seen them. They've not been able to be created in particle accelerators and things like that. And so if, like Victor's saying, that this theory that maybe it comes from a different dimension, well, maybe that's why we don't see these particles, because those particles exist in a different place and we're just seeing the effects of them, right? Or the remnants of their interactions here in our universe. But that'd be kind of interesting. What else do you know about gravity?
Mass causes gravity.
Okay, so it has something to do with masses, and the more massive an object is, the greater its gravity, and that's pretty well understood. I think even if you just look at like the solar system, the fact that things are orbiting the sun as opposed to the Earth because the sun is so much more massive. Good. So it definitely depends on mass. And basically, the way what's going on with gravity is that any two masses exert a gravitational force on each other. And these forces, they're not contact forces. You don't actually have to be in contact for gravity to occur. And I was going to say, we haven't talked about this, but you may know this. All the forces that we've talked about so far require some sort of contact. There's a push or a pull physically going on, right? With the exception of gravity. Because when I take this pen and I drop it, when I let go of it, right, gravity pulled it down, but didn't actually touch it. As opposed to me lifting the pen up, it's going up because I am applying a force directly to it, right? So those we call field forces. So I'm going to go ahead and write this up on the board, but I'm going to come back and talk to you in a second. But let me just share some things real quick. So gravity is what we call a field force. And there are a bunch of these. But field forces don't require contact. All that they require is that you are, well, near each other, but even near each other is kind of subjective, but they don't require contact. And they're what we call inverse square. They follow the inverse square law. And so basically this is what it would look like. So our force, our field force, there's going to be some constant of proportionality. And then it's going to be dependent upon the square of the distance between the two objects. So if we've got object number 1 and object number 2, right, D is just the distance between them. So field forces are inverse square laws. The reason that they're an inverse square comes from geometry. If you look at basically the energy that's coming out from one, so let's just say we've got some force that's emanating out. The strength of that force has to cover a sphere, because if we go the same distance away from a point in space that creates a sphere, all that energy gets spread out over a sphere, and spheres, that's a surface area, and we know areas are related to a distance squared, so that's what this is coming from. But anyway, so field forces don't require contact, and gravity is one of these. So let's come back to me chatting here with you. All right, so we don't actually need contact, which is a little bit weird. And you haven't experienced this before in physics, but gravity's not the only one. We're going to see, like I mentioned, the electromagnetic force. Magnets, you don't actually have to be in contact for them to affect each other. And you may have seen that playing around with magnets back in the day. You can actually make one move by bringing another one close to it, right? So magnets do that. Electricity works that way, electrical charges, but also nuclear forces, the things that actually hold nuclei of atoms together, are field forces and so on. So anyway, so gravity is a field force, which is also a little bit different, right? So any two objects actually exert a gravitational attraction on each other. And you notice I said they attract each other. And I'm saying that because of Newton's third law. Remember good old Newton's third law, the for every reaction, there's an equal and opposite reaction, or at least that's the way a lot of people will say it. So think about this, and I bet you've never thought about this way, but I take this pen and I let it go, and it falls towards the earth because it's getting pulled towards the earth by gravitational field. Well, by Newton's third law, that's saying at the same time, the earth is getting pulled towards the pen. So I don't know if you've ever thought about this, but anytime you've ever fallen and you say, oh no, I fell down, you did fall down, but at the same time, the earth fell up. The earth came up towards you, And so you didn't actually fall the full distance. Some of that distance got shortened by the Earth coming towards you. Kind of trippy, huh?
Yeah, that's
But
pretty.
Is it is it a minute distance?
okay, we are going to see that the actual acceleration that when you fall, the actual acceleration that you're applying to the Earth is super tiny, super tiny. So that if you then use that and even go to your kinematics using a constant acceleration, that your change in position of the Earth is going to be super, super tiny. So kind of like what Victor just put in the chat, he wrote 0.infinity centimeters. Yeah, it's going to be 10 to the minus so many minuses that it's not even noticeable. So, but we'll do, as soon as we kind of get the formula for gravity and how it plays out, we'll check that. We'll see how minute that actually is, right? Whereas for us falling, it's significant. 9.8 meters per second squared. That's enough for us to move pretty quickly and often with really bad results, right? As we were talking about compression factors and stuff like that, we can really hurt ourselves because of gravity and how Earth moves us as opposed to us trying to move the Earth. Okay, so kind of the historical development of this is that forever, humans have known that things fall towards the Earth, right? I guarantee you this experiment has been done a bajillion, and that's actually a technical term, a bajillion number of times, and in fact has been performed by people before written history, and was well known what the result was going to be, right? So gravity's been known forever. Now, here's what I like. Way back in the day, like in the time of Plato and Aristotle and stuff like that, that was back when they thought about the elements, right? That there were the four elements: earth, fire, wind, and water, right? Air and water. So you had the four elements. And I forget who it was. I think it may have been Plato. Don't quote me on this, but it was one of those. His thought was that things that are earth want to go back to earth. They want to go back to the earth. So that's why if you take a rock and you take it up here and you let it go, it doesn't want to be in air. It wants to go back to earth. And so that's how they started classifying things in the earth category as things that were going to go back to earth, right? As opposed to like fire. Fire doesn't want to go back to earth. Because think about what we see when we burn something. Where does the fire go?
Up.
Yeah, it goes up, right? We see those flames go up. We even see the cinders and the sparks, and they all go flying up. So obviously, what is fire attracted to? Well,
Wind.
Fire is going to be attracted to the wind element or the air element. It's going to want to go there, right? And then water, similarly, water is going to want to go to earth. Obviously, why? What would tell you that?
Lakes, rain.
Rain, yeah.
Water.
I mean, if you've ever been outside on a rainy day, obviously the rain element, the water element, wants to get attracted to the earth element. So, and here's what I love. The reason I like bringing this up is, a lot of times we look at those old-timey folks and we go, ugh, what idiots. Can you imagine that they thought that the earth was made up of these four elements? And, right? Obviously, they didn't have the knowledge that we have. They didn't have the centuries of scientists and data acquisition and all that. So you got to cut them that break. But if you do that, if you just go with, okay, they didn't have what we have. They still had a brain. And they still thought about things logically. And they still tried to put order to the universe. And it makes total sense. It really does. If you go to those are the four elements, it makes complete and total sense to say, oh yeah, water is going to go to earth, as is earth, and so I think it's really interesting to see how even though their perception of things was different, or it was based on different things, they still came to similar conclusions using what I would say is kind of the scientific mindset. So this is another reason why I really like mythology, because mythology is the same thing, right? Like you go to all those Greek myths and all that about, you know, like Iris is the god of rainbows and all this. You know, they were just trying to do what we do. They were trying to describe what they see and explain why the things out there happen. And they were just coming from a different place, right? So anyway, so to me, science, philosophy, religion, it's like, it's all the same thing. It's just different sides of the same object. But I'm starting to preach. So let's get back to gravity. So that was the original thought. And then, of course, people started figuring out that there was a little bit more to it, right? Like the whole things orbiting the Earth idea, the Earth-centric universe, that came about long before Newton came up with his theory of gravity, because then after that came the, well, no, it's actually heliocentric, and all that was kind of put together. So there was kind of this evolution to this point, but finally Newton kind of put it all together and realized the structure, this inverse square structure. And so this is how he put his law of gravity together. So let me go to the board again. So we've got Newton's law of gravity. It is a law, which means it's pretty much as true as anything can be. Obviously in science, we never prove anything, we support. But the law of gravity has been supported so well that we're pretty much sure that it's the way that it works. Now, could there be other parts of the universe where this doesn't work? Sure. I don't know. I've not been to those places, but everywhere we've seen, it definitely seems like it applies. So here's how we get this. So the force due to gravity, it's actually equal to some constant. So we're just going to call this guy big G for right now. So it's the gravitational constant times m1 times m2 over r squared. And so what these things are, m1 and m2 are the masses of the objects. So if we're talking about, say, the pen that I'm dropping and the Earth, so mass 1 would be the mass of the pen, mass 2 would be the mass of the Earth. And then r, this is the distance between their centers of mass. And this is actually really important, that it's the distance between the centers of mass. So like when we're talking about this pen, it's not the like 1.5 meters that it is above the surface of the Earth. It's actually the distance from the center of this pen, center mass of this pen, to the center of mass of the Earth, which for all intents and purposes is the center of the Earth. So we're actually talking about thousands and thousands of kilometers, right? So it's actually a significant distance. Okay, so Newton, his thought was that it is definitely proportional to the product of the masses, but also inversely as the square of the distance between them. And then he put this big G on here because he knew it was proportional, right? And we do this all the time where we don't know exactly, but we know that it's off by some sort of a factor, right? And so that's what that G was. So Newton came up with his idea and it started explaining everything they saw. But of course, the next big thing was, how do we calculate G? We need to get that number. So here's how this came about. So there was a scientist by the name of Henry Cavendish. He was English. And Cavendish came up with this great way of figuring out this constant. So here's what he did. He basically took two really, really, really massive objects. They weren't super big, but they were massive. So think something that's really dense, like lead or gold or something like that. But so he created, he got two really, really, really big masses like this. And then he suspended them by really, really, really fine strings. So think really, really thin, like hair follicle thin. And basically set them up so that they could rotate. So think about like a dumbbell. So we've got like two really big masses that are then connected by something in between. And that's hanging from a string so that it can just kind of rotate. So he puts it in position and then brings another really massive object nearby. So what's going to happen is that massive object is going to make this thing want to turn and rotate. So what he measured was actually the rotation. He looked at the rotation of this and then was able to figure out the force that was causing it by basically using moments of inertia and torque, right? So he took this rotational thing, turned it into the linear force, and used that to get a ballpark number for G. Now, I want to say this was in the 1700s. Again, don't quote me exactly on the date, but it was a long time ago. And they actually got really, really close to what we now know as the accepted value for G. Obviously, as time has gone by, as we've gotten things that are better at calculating, better at measuring, we have more precision, we're able to get a better number for G. But even a couple hundred years ago, they had a pretty good idea of what this gravitational constant needed to be. Okay, so big G. Let me put it on the board. So big G here. So I gotta switch pens. Big G, this is called the universal gravitational constant. So this thing, the value for big G is 6.67. There are a whole bunch more decimals after this, but this is as far as I'm going to go. So it's 6.67 times 10 to the minus 11. And I intentionally didn't put units on there because I want to see if you guys can tell me what the units need to be. What do the units need to be on this?
Meters per second squared.
There's a little bit more to it than that. And I'll give you a hint. Go back to the formula, because the formula will help you figure this out.
So kilograms. Meters per second squared.
So we need to end up with newtons, because it's a force. At the same time, we need to cancel out some kilograms. And we also need to cancel out some distances. So this is going to be Newton meter squared per kilogram squared. So there are the units on this. It's Newton meter squared per kilogram squared.
How the fuck did he solve that? Jesus.
Nah, what do you mean? Like, we know what these
No,
are.
I don't
Obviously,
mean the units. I just mean that number for
okay, because it is really small, right? So, you know, basically, you're just looking at how much this rotation is happening. And what he actually did was he used light to help him. So, like, remember I was telling you, you got this thing that's rotating.
Like cracks, how it.
So if you have like you know, like a mirror up here that you're shining light on, you can see where the reflection moves to.
Yeah.
Light, especially if you have like a pretty good beam, he didn't have like a laser or anything like that. But if you have a really thin beam, you can go far away which then lets you measure your angle, or get your angle a little bit better.
Refraction he used refraction of light to get an angle. Like, I'm trying to like tease it out of my brain how he did that.
Yeah, so he was looking at.
How do you even think of a question like that?
Well, that's the brilliance of Henry Cavendish, right?
So,
so I think about it this way. All right, so I'm shining. Let's say we've got a laser, okay, and obviously not in 1700s, but say we've got a laser. So I shine a laser, it bounces off a mirror, comes back, and I've got a screen and I can mark where that laser hit. Now, as this thing is rotating, right, as my little, dumbbell looking thing is rotating, that's causing my mirror to rotate, which means my beam is bouncing off and now coming to a different place. So again, on this screen, I measured at the beginning, the beam hit here. A little bit later, it hit here. So I can look at this distance separation, and if I know how far away that mirror is, that gives me an idea of an angle, right? The angle to those two. Then looking at that angle, I now have an angle that I know how far it changed over time. So there's an average angular velocity.
Okay.
Which then I should know the moment of inertia of my thing, because I've got two solid spheres with a really lightweight something, whatever. I can build my moment of inertia like I normally do, which then means, okay, from moment of inertia and omega, now I can figure out the torque. So that's the torque on this thing. What's causing it to spin? Well, what's causing it to spin is this gravitational force. I know how far away from the axis of rotation it is, so I can translate that torque into a force. And okay, well, now if I know my force, then I go back to this formula. I know the two masses, I know their separation, and I can calculate my G. So that's the logical step as we progress through. But I agree with you, Ian. I think really what you're getting at is, who thinks up this kind of thing? Who thinks up, this is how I'm going to test it, and then does it? And that is the beauty of the human mind, right? Yeah. Is that we have people that are creative like this and come up with the most insane ways of testing something, right? And that's why we know this guy's name. Right? Think of all the physicists in the history of physics. We don't know a lot of their names.
Yeah.
Right? I mean, how many of those names have you even heard? A couple dozen. Right? So we're talking like the ones that, the cream of the crop, the ones that have that magical spark. It's the same reason we don't know every composer in the world, but we all have heard of Beethoven. Right? It's the same kind of deal. It's just in the science world. All right, well, now we've got G. Now it's a piece of cake to do stuff. So let me actually show you how we can get little g. The gravitational acceleration, 9.8 meters per second squared for us here on Earth. Okay, so let's go back to the board.
Real quick, this big G, is that throughout the entire universe?
It is a universal constant. So if we're going to try to calculate the gravitational attraction between Saturn and Neptune, we're going to use that same big G, but with their masses and their distance. If we're going to look at the gravitational attraction between two black holes that are on the far other side of our the universe, same thing. We still need to know their masses, and we need to know how far apart they are. And then we could actually calculate F.
Okay.
So
that's cool.
It is cool. And this actually brings me up to something else that I want to talk about. It just reminded me.
And you just made me read, like, I'm going to try to read an article now on the Cavendish experiment.
Cavendish, yeah.
Yeah, he created an apparatus that was allowed him to solve this.
Yep. Yeah, they call it a torsion balance.
Yeah, torsion
Because
balance.
torsion means torque, right? So it's a torsion balance. It balances torques. It's getting itself, instead of like a weight balance, it's a rotational balance. So it's a torsion balance. But yeah, check it out, Cavendish. Let me put his name here in the chat just so y'all can see how it's spelled.
If I find a good site, I'll link it too.
All right, cool. But this just made me think of something else. Like, think about a black hole. So we know black holes exist, not because we can see them, because we can't see them. It's impossible to actually see a black hole. But we know they exist because of their gravity, their effect on other things, their gravitational effect on other things. We see how stars are moving towards a black hole, or something like that. Well, that's actually how we figure out the mass of a black hole. Like, I don't know if you've ever wondered this. Like, you go look up in a book, or you go onto Google and say, or hey, Alexa, what's the mass of the sun? Right? And then Alexa will come back and say, oh, the mass of the sun is blah. Have you ever wondered how we know that? Because I don't know about you, but I've never seen a scale.
I'm assuming we didn't put it on a scale, yeah.
Yeah, I've never seen a scale big enough to put the sun on, or gee, let alone the moon, right? I mean, we still have a pretty good idea about how massive the moon is. So how the hell do we figure that out? Well, this is another case of like reverse engineering. Take like the moon, for example. We know how fast the moon is traveling around the Earth because we can measure that. Right? We know the amounts of time. We can get a decent idea of how far it is, right? All that good stuff. Just so you know, Ian just posted a link to something about the Cavendish experiment that comes from Harvard, which is probably a pretty reputable source. But
yeah,
I mean, it's only Harvard. It's not like it's Colorado State University or something. So
it was the best one that was on there. I looked.
Sounds pretty iffy to me. I mean,
yeah, right.
From Colorado State.
Oh, wait, Colorado State is iffy? You watch your mouth, young man.
No, I said it's not from Colorado State,
right.
so it is.
All right. Anyway, so like basically we figure out the forces that are acting on, say, the moon by looking at its motion. Well, then we know where's that force coming from. Well, it's coming from gravitational force of Earth. Well, if we know the gravitational force and we know the mass of Earth, which again, we got to know something, right? But then we can kind of, again, reverse engineer, and next thing you know, we've got a mass of the moon. Well, this is how we figure out the mass of planets, of suns, of black holes. We're really just watching their effects on other things. How are they pulling other things by gravity? And then we can do that. So all of astrophysics, everything we know about astrophysics, if it weren't for this law, this Newton's law of gravitation, we wouldn't know squat about the formulation of the universe. So something really simple. I mean, it's a really, well, I was going to say it's a real basic equation. It doesn't look that basic because there's a lot of stuff in it, but it's not that complicated, really. Something that simple we use all the time when we're trying to explore the universe. So let's do this. Let's see where little g comes from, that 9.8 meters per second squared. And at the same time, we'll look at how much of an effect we have on Earth, right? So like I was saying, when we fall, Earth is pulling us, but we're also pulling the Earth. We'll do that at the same time. So let's go to the board. All right, so let's go look at this with the Earth and us. So I'm just going to change these so that it's more applicable to us and the Earth. So I'm going to let one of the masses be the mass of the object that's falling towards the Earth. So the pen, us as we fall, baseball in the air, whatever. That'll be M. And then the other one, let's call this ME. Okay, so that'll be the mass of the Earth. So then if we want to look at the distance between the centers of masses, that's really going to be the radius of the Earth. Now, technically it's not, right? It's not quite the radius of the Earth, but it's pretty close, and especially if we're near the surface. And that's the assumption that we've always made when we use that G equals 9.8, right? It's always that we're near the surface. We're not talking about using that G if we're up at the International Space Station or anything like that. Okay, so we'll call it close enough. Now, technically, what we would want is we would want R of E plus H, where H is our height above the ground, above the surface of the Earth. But let me just show you why mathematically we can ignore the rest of it. So if we go to this, we get RE squared plus 2 REH plus H squared. So again, just think about this. The radius of the Earth, it's 4,000 some miles. The H we're talking about, how far we are from the center of the Earth, is tiny. I mean, even if we go to the space station, that's only a couple hundred miles, which compared to a couple thousand miles, it's still like 5%, something like that. So this is going to be pretty small, as is this one. Since we're multiplying this big number by a small number, it's going to be considerably smaller. So technically, it should be RE, the radius of the Earth, plus our height above it. But for right now, we're going to go with, nah, it's close enough that it's just the radius of the Earth. Okay, so let's plug in those numbers. So I know that we got these numbers the other day. I don't remember what they are, but let me see if I can find them here real fast. The radius of the Earth is 6.4 times 10 to the 6 meters. So that's going to be our radius of the Earth. And then the mass of the Earth is 5.97 times 10 to the 24 kilograms.
So real quick,
Yep, go for it.
I'm sorry, but I remember when we did the mass, when we were finding the center of mass between the Sun-Jupiter system, the mass of Jupiter was 10 to the 27, and that's only 1,000 times larger than the Earth. Even though it's like bigger, it's not as dense, correct?
Correct.
And that's why it's not that far apart in size, or mass, I should say.
Yes. If you look at the densities, the density of Earth is greater than Jupiter. And that's because Jupiter is, well, mostly gas.
Yeah.
Gases are less dense. Earth is primarily solid, right? I mean, it's rock for the most part. There is liquid rock somewhere in the insides, but that's definitely more dense. Yeah. In fact, I don't know if you know this, but Saturn is, its density is so light that if we had a big enough tub of water, Saturn would float. Saturn would actually float in water. Kind of crazy. All right, so here are our masses. So let's think about how we're going to use this to figure out not big G, but the little g. It's our gravitational constant here on Earth. So remember good old Newton's second law is that this is equal to mass times acceleration. So here's the pen falling. Its mass is m times the gravitational acceleration g. So notice that that mass doesn't matter. We can actually cancel that out. And that's why we can actually apply the same g value to any object that's falling. So on the surface of Earth, this g that we know and love, it's actually going to be found by taking the gravitational constant, big G, times the mass of the Earth and dividing by the square of the radius. So let's do that real quick on our calc. All right. So we're going to take that big G that we saw before. We're going to multiply that. Hold on a second here. So 6.67 times 10 to the minus 34 times the mass of the Earth, so 5.97 times 10 to the 24. And then we're going to divide by 6.4 times 10 to the 6th squared. Before we go too far, just look at the order of magnitude that this is going to be. So we have 10 to the minus 34 times 10 to the 24 over 10 to the 6th squared. And so even if you just look at order of magnitudes, we're going to get minus 10 here, right? And then we're going to get 12 here because 6 times 6, 12. Right? And so what we should end up with is something on the order. I totally botched something here. I totally messed something up.
It's the first one. It should be 10 to the negative 11.
Ah, there we go. Thank you. That's better.
Yeah.
Because then, there we go. Yeah, so that gives us 13 on top. And then 13 divided by 12. That's, so that'll be 13 minus 12 is 1. So we're going to get something on the order of 10. 10 to the first. All right, so I run this on my calculator, and I get 9.72 as my G value. All right, so you might look at that and go, oh, that's still pretty far away from 9.8. Why do you think it's off from 9.8?
Decimal approximation and not a full decimal at that.
Yeah, if I carry this out, I go more decimals on each of these things, that will actually get me a lot closer to the 9.8. So Victor just put on the chat the H. Sorry about that. The H actually doesn't really impact it that much. But another thing that does is the radius of the Earth. Because we also know that the radius of the Earth isn't constant. It changes depending upon where we are. So that would be a little bit of it as well. Anyway, so this is where that G is coming from. It's just doing Newton's law of gravity. All right, well, now that we know how much Earth is pulling on us, let's do the same thing, but look at how much we're pulling on the Earth. So in terms of the Earth, it's still the same force because of Newton's third law. But now that's going to equal sorry about that. I just got muted. All right. So let's come back to this again. So we've got the mass of the Earth times A. But now those Earth masses cancel. So if you want to see the acceleration that we're applying to the Earth, that's going to be G times our mass divided by the RE squared. Okay, so let's take something that's a little bit smaller, say, than the Earth. And let's just go with something easy. Let's go with something that's 100 kilograms. So we've got 100 kilogram mass that's falling. So what is that, like 220 pounds, something like that. So let's just go 100. So now the acceleration that we have on the Earth is again going to be that 6.67 times 10 to the minus 11. But now let's go with a whopping 100 kilograms. So that's not a pen, right? I mean, that's something big. But then we go ahead and divide by this radius again. Well, just look at the order of magnitude on this. We've got 10 to the minus 11 times 10 squared divided by 10 to the 12th. That's going to be like 10 to the minus 21. So I get 1.6 times 10 to the minus 22. So that's how much a 100 kilogram object would be pulling on the Earth. That's the acceleration that the Earth would feel. Okay, this is why we don't notice it.
It's very tiny, huh?
Very tiny. And like I said, if you were to go and do the kinematic equations to go figure out how far the Earth moved, so you just assume that constant acceleration for however much time we have as we're falling, which is going to be a short time. But if you were to do that and calculate it, you'd see that it's so minute that you wouldn't even notice. All right, but any two objects could do that. Okay, ooh. So Victor just said, how many of us should jump up together to get
Actually,
a chance?
I remember like hearing that there's a video where the guy like talks about what would happen if everyone on Earth jumped at the same time. I haven't seen it, but it sounded interesting, and it just
Well,
It was in Vsauce video. I actually know the one you're talking
yes.
about. Yeah.
well, I'll tell you what. Let's calculate it. Let's make at least a reasonable guess. And this would be if all of us were together at the same place, which is already kind of hard, right? Because just the density of people would be a little difficult. But let's just change this. So now, instead of a mass of 100 kilograms, what do you think the average mass of a person is in the world?
50.
50?
What, like 100?
Around 50 kilograms or something like that.
I'd guess more, right? Because average male and female. Well, I just looked it up. Female is 50, and then male is 70. So it'd
Okay,
be.
but that's adult.
Oh shit, you're right. So it'd be
Right.
even less.
So let's go
I think
50.
50 kilogram is a good estimation.
I think 50 is probably fine to account for all the children, right? And if we go with, you were saying, so the average female is 50, and then the average adult female, and the average adult male is 70. I think we can probably account for all those adult male, bring that down with all the children. So let's just go 50 kilograms. So we're going to go with every person weighs 50 kilograms. How many people we have on Earth? 7 million?
7 billion.
7.5 billion. About.
So we're at 7.5.
I think so. Let me look it up.
Yeah, I'm pretty sure it's 7.5 by now.
All right. Well, let's go with
7.8 billion people.
Okay.
Wow.
Let's go to 8. We'll just make life easy for us. So we're going to go that we've got 8 billion people. So that's 8 times 10 to the 9. And each of them weighs 50 kilograms. So that's going to give us 400 times 10 to the 9, which is 4 times 10 to the 11. So all of humanity weighs 4 times 10 to the 11 kilograms, more or less. All right, well, we're going to put that in here for our mass. So instead of the 100, let's put 4 times 10 to the 11. And even if you just do dimensional analysis, what are we talking on the order of? We got 10 to the minus 11 times 10 to the 11 divided by 10 to the 12.
It's -12.
Yeah, it's going to be on the order of like -12, off a little bit depending on what the numbers are. So let me just throw this into my calculator real quick and let's see what we get. .5 times 10 to the minus 20 or 13.
I guess this is like a conceptual question, but like, so I'm like trying to let's say we keep birthing, right? But isn't like Earth's system of energy and masses like within itself, if that makes sense? Because like human eat and then sure we create a kid, but it's all part of Earth's matter. So it's like all its own system of matter. Because we're not gaining things from outside normally. We are somewhat, asteroids and things, but like I'm trying to think of a way to explain it. Is like human are always part of Earth's mass, if that makes sense.
I think I know where you're going. Let me see if I can kind of dissect this a bit. Okay, so when we talk about the mass of the Earth, you're saying that should include humanity.
Or just like all things upon it.
Sure. And probably like when we get this number for mass of Earth that was 5.97 times 10 to 24 kilograms, yes, that includes me. And that includes you. And that includes, the dog that's running outside here. And that includes the fencing material for my backyard. And yeah, that includes all of that. So technically, we would probably need to reduce the mass of the Earth by the mass of all these people. But you take something like 10 to the 24th and you remove a 10 to the 11th, you don't even notice that.
Yeah.
Right. But now also are we gaining mass? We are absolutely gaining mass. You mentioned, asteroids, so meteors. Meteorites definitely add to the mass of the Earth. But sunlight also adds to the mass of the Earth.
Also losing mass though too, right? Because of solar wind and stuff stripping away.
We also lose mass, absolutely. Like the atmosphere, we lose things from the atmosphere all the time. There are molecules in the atmosphere that are moving fast enough that they escape from Earth. So there is fluctuation, but that change is pretty tiny, either the increase or decrease, especially when we're talking on the order of 10 to the 24th. Like you're not going to notice that. But in reality, yes, Ian, that does.
Yeah, I guess it's kind of like living organisms and changing things is just like a transformation of Earth's matter already.
Yeah. And what you're going to learn when you get to fourth quarter physics is that mass is actually part of the conservation of energy, because energy can get turned into mass and vice versa.
Yeah.
And so that, yeah, it really is that, like when let's just take a child grows up, right? And they become more massive as they're getting larger. That's coming from other sources of mass, right? It's the foods that they eat, the water that they drink, the minerals that they're getting from all that sort of stuff get then put into the body and become bone and muscle and fat and all that other stuff, right? So it's really just a shift of where the material is, or the form of the material. So anyway, so there you go. What would happen if all of us jumped at the same time in the same direction?
Not much.
The acceleration was 6.5 times 10 to the minus 13 meters per second squared, which you take that and you multiply by the mass of the Earth, you still get a pretty good force. It's a force, like 10 to the 11th kilograms, but it's tiny acceleration. So would it be noticeable? There would be devices that could notice that, but like us, if the Earth right now all of a sudden went through an acceleration of 10 to the minus 13 meters per second squared that you weren't prepared for, you wouldn't notice it. It wouldn't even feel like an earthquake. You wouldn't even notice anything. So
That's sad.
all right, well there you go. So who needs Vsauce? We can do it ourselves. All right.
So an earthquake, I know that's tectonic plate movement, but is tectonic plate movement due to gravity pulling things towards the center of the Earth?
Tectonic plate movement it's actually due to the circulation of the liquid rock inside the Earth. Think about, I'm trying to think of a good example. Like, okay, have you ever made something like, like chicken noodle soup or something like that, and it forms like a film on the top of the water?
Yeah.
Right? And then as the water boils, you'll see that film kind of move around. That's kind of the same thing that's going on with tectonic plates. So the Earth has these plates, it's like the crust. They're not solid. I mean, they are solid, but they're not joined together per se. And so they're able to kind of wiggle around. Now, if we've got stuff kind of just rolling around on the inside, it's going to want to pull things apart, move other ones together, right? And that's what's actually causing the tectonic shifts that cause earthquakes. So that's more of a fluids / thermodynamics kind of thing. So we'll probably revisit that as we move along this quarter. So anyway, all right, so good for that. Kind of interesting, right? This idea of gravity and that any two things are attracted to each other, but it really describes all motion. So let's talk about some specifics here, and then we'll take a break. And I think next time you see me, I'll be in my garage. We'll talk a little bit about rotation. But while we're on this subject, let's just talk about a couple more things that have to do with gravity here in this context. And the first is going to be, suppose that we want to send something away from Earth. So we're going to go launch a rocket or something. My question is, how fast does it have to move for it to escape? Right?
Depends on its mass.
Right, to get past the Earth. Okay, so will it depend on how massive it is? Maybe. I mean, in terms of what kind of force we have to apply, obviously, the more massive it is, the more force we have to apply. But let's see if we can figure that out. And to figure that out, we need to talk about gravitational potential energy a little bit better than just good old MGH, because that really only works when gravity doesn't change. Let's go back to the board. Because think about this little g that we even calculated. Remember when we calculated that little g, we were using the radius of the Earth. But obviously, if we're further away than the surface of the Earth, the gravitational attraction we're going to feel is going to be lessened. Like, let's do this. I'm going to keep the mass of the Earth up here on the board. But let's say we're not looking at gravity here, but maybe let's look at gravity on the International Space Station. Okay, so we're going to be in orbit about the Earth, and let's actually look and see what kind of gravity we'd feel there. So obviously what we're going to need to know is the height of the orbit of the International Space Station. So I'm going to real quick do a Google search because I don't know that number off the top of my head. But let's just see here. So how high is the ISS above the Earth? All right, so my Google says that it's about 400 kilometers above the Earth. So if we're going to look at the ISS, its R then is going to be the radius of the Earth plus 400 kilometers. So that might not feel like that's enough to make a difference, but it is. Like when we go back to the radius of the Earth, right, that was times 10 to the 6th, so 6.4 times 10 to the 6th. So now our R is going to be 6.4 times 10 to the 6th plus 400 times 10 to the 3rd, or 400 kilometers. So this is actually 4 times 10 to the 5th, which is enough to make this turn into 6.8 times 10 to the 6th. And you guys have enough experience with numbers and everything now to recognize that this is going to be significant. It's not quite 10%, but it's like a 6.5% increase or something like that. So now if we run the numbers, so we'll use the same G, we'll use the same M for the mass of the Earth. Let me just put it in my calculator here real quick. We got 5.97 to the 24th for that mass, and now 6.8 times 10 to the 6th. User error. All right, I get that the gravitational, I'm going to call it G, but I'm going to call it G sub ISS, is 8.6 meters per second squared. So it's significantly less. It's not 9.8. It's more like 8.6. All right, well, that brings me to another thing. I keep going off on tangents today, but I guess that's what happens when I talk gravity. So here's another
And it's Friday.
And it's Friday. Here's another misconception. And you'll hear people talk about this all the time. They'll talk about, like, if you're in the space station, that you're in 0G, that there's zero gravity. That's not true at all, right? In fact, there's a fair amount of gravity. You're still being pulled towards the Earth at 8.6 meters per second squared. So what we consider, what we say when we say 0G, what we're saying there is that what is actually happening is that you're in free fall. So the International Space Station, it's really always falling. I know that seems weird, but go back to that idea when we were talking about things spinning around in a circle, like the good old pail of water that's not spilling, or, you know, whatever. And remember that in order to stay in a circle, there has to be a force that's pulling you towards the center, because otherwise you just go flying off. Well, that's what gravity is doing. Gravity is that centripetal acceleration that's keeping us from falling in. All right, so they're basically on the space station constantly falling, which I think is kind of trippy to think about, but they're just constantly falling towards the Earth. But falling towards the Earth, because of how fast they're going, keeps them in an orbit. And we can actually calculate how fast that is, how fast they have to be moving to stay in an orbit that's that high. But they're just always falling. So Jesus just put there, you know, and say, is that what they call the G-force? So G-force, what that is, when they talk about 5Gs or 2Gs or something like that, that's the number, or that's how big the acceleration you feel is. And when we say 2G, that would mean it's twice regular gravitational acceleration. So like right now, all of you are experiencing, well, technically you're experiencing 0 Gs, because you've got your seat pushing up against you gravity's pulling you down. You're not accelerating. But if we just think about because of gravity, we're actually feeling 0, or we're feeling 1g. Now, when you get launched up into a rocket, think about what happens. Now that rocket is pushing up on you. So you feel it pushing against you, which makes you feel like you're pushing down more, which is going to feel like you're heavier. That would be you're feeling more than 1g. So if you've ever been on an amusement park ride where it feels like you're getting sunk down into the seat, what's happening is that actually the seat is pushing up on you, but you're feeling like you're coming down because it's a perception thing. But the strength of that acceleration, if you were to divide that by 9.8, that would tell you what g-force you're experiencing. And the same thing if you go on something that spins, like that, to be honest, that's one of my favorite amusement park rides are those ones, they're called like cyclotron or something like that, where you go in and you kind of lean up against the wall and then it starts spinning and you start like sliding up towards the top. And then you feel like you're getting pushed against the wall. Those are fun. Go try to do push-ups in those. That's always good. But that's, again, centripetal acceleration has been increased and you're feeling more G's, which is letting you like stand up against the wall basically, instead of falling. So Victor, you just said 0 gravity will make them go away or fall. Well, 0 gravity just means either can happen. And that's why they just sort of float there. Like if you watch video of the folks that are in the ISS, they just kind of float there, where you see the water blobs that are just there, just kind of dangling. And of course, if you give them a little push, they'll start moving because you just gave them an external force, but that's not due to gravity. Gravity's only role in terms of the space station and people in it is to make them continually fall. If gravity were to turn off, then like if all of a sudden Earth's gravity stopped for whatever reason, then they and the space station would continue just to keep flying and would go away from the Earth. So in terms of actual 0 gravity, if we're talking about 0 G's versus 0 no gravity, no gravity would be a very bad thing for folks in the space station because they would never come back to Earth. Anyway, I digress. You know what? I think at this point, let's take a break.
Probably be bad for everybody.
Yeah, if gravity went away right now, yeah, really, really bad things would happen. Now, we luckily, we would still have, well, because of the rotation of the Earth, we would still experience a little gravity feel. It wouldn't be enough for us to do anything. But I think the bigger issue would be if the Earth quit rotating. That'd be really bad. But I'll tell you what, let's take a break. Let's come back in 10 minutes at 4:30. I will meet you guys in the garage because I want to show you, I just want to show you some stuff with angular momentum and conservation of angular momentum, something I would have shown you on campus and would have let you experience, but I'm going to have to do it myself. But I'll see if I can get my, my science buddy to help me out a little bit. He probably will want to do this because it's fun. So I'll see you in about 10 minutes, all right? And expect me on the other screen because I'm going to take my phone with me. I'm not going to bring my computer. But you'll know I'm back when you see the non-beer drinking picture. All right, so I'll see you guys in 10 minutes.
All right, see you.